Physical significance of logarithmic decrements. Okay, physical significance of logarithmic decrements. The logarithmic decrements of a damped oscillatory system gives the measure of the rate at which the amplitude of vibration decays. Okay, that means as a logarithmic decrement, physical significance of logarithmic decrement. The logarithmic decrement, the logarithmic decrement, the logarithmic decrement of a damped oscillatory system, of a damped oscillatory system, damped oscillatory system gives the measure of the rate, gives the measure of the rate at which the amplitude at which the amplitude of vibration decays. Okay, as logarithmic decrement, as logarithmic decrement lambda equal to pi r by m omega dash, that is r by 2m into t. It gives a method of evolving of uniting are the damping constant. Okay, next is relaxation time. Okay, relaxation time. What is relaxation time? The relaxation time is defined as the time in which the amplitude of the damped oscillations falls to 1 by e of its original value. Okay, the relaxation time is defined as the time in which the amplitude of the damped oscillations falls to 1 by e of its original value. Okay, if a naught is the amplitude which becomes a equal to a naught by e in a time tr, that means tr is relaxation time, as the value of 1 by e is 0.368, the amplitude of a damped oscillator falls to 36.8% of its initial value in a time relaxation. Okay, relaxation time. Higher is the relaxation time. If higher is the relaxation time, slower is the rate of fall of the amplitude of the damped oscillator. Okay, at any time t is given by a equal to a naught e to the power minus bt, where b is the damping coefficient. Okay, and t is the relaxation time, and if t is the relaxation time, then a equal to a naught e to the power minus bt, that is a naught 1 by e to the power minus 1, that is e to the power minus bt r equal to e to the power minus 1, that is btr equal to 1. Okay, btr equal to 1. Okay, If BTR equal to 1, that is the relaxation time TR. That is relaxation time TR. The R relaxation time TR, relaxation time TR equal to 1 by B. Okay, it is clear from equation number first. This is equation number first. It is clear from equation number first the relaxation time varies universally as a damping coefficient. Okay, it is clear from the equation first. It is clear from the equation first. It is clear from the equation first that relaxation time varies inversely as the damping coefficient Okay, next, relaxation time of mechanical oscillator. Relaxation time of mechanical oscillator. Okay, relaxation time of mechanical oscillator. Okay, relaxation time. Next is relaxation time. Second, first point, relaxation time of mechanical oscillator. Relaxation time of mechanical oscillator. Mechanical oscillator. Okay, for a mechanical oscillator, for a mechanical oscillator to be equal to R by M, where R is the damping constant, where R is the damping constant, okay, then B equal to R by 2M. Hence relaxation time for a mechanical oscillator. Hence relaxation time of a mechanical oscillator is 1 by B, that is 2M by R. That is 2M by R. Okay, and thus relaxation time is inversely proportional to damping constant. Thus relaxation time is inversely proportional to damping constant. Inversely proportional to damping constant. Okay, damping constant. Second point, relaxation time of electrical oscillator. Relaxation time of electrical oscillator. Okay, next is relaxation time of electrical oscillator. Okay, relaxation time of electrical oscillator, that is Q equal to Q naught e to the power minus BT. For T equal to relaxation time TR is 1 by V, that is Q equal to Q naught e to the power minus 1, e to the power minus 1, that is q naught by e. Okay, for an electrical oscillator, to be equal to capital R by L, where R is the resistance and L is the inductance. R is the resistance, and L is the inductance. Okay, of the circuit. Hence the relaxation time for an electrical oscillator, hence relaxation time TR equal to 1 by B equal to 2L by R. 2L by R. Okay, 2L by R. Okay, thus relaxation time is universally proportional to the resistance of the oscillator circuit. Thus relaxation time is universally proportional to the resistance of the oscillator circuit. The resistance of the oscillator circuit. Resistance of the oscillator circuit. Okay. Next, relation between logarithmic decrement and relaxation time. Next is relation between logarithmic decrement and relaxation time. Okay. Then that is relaxation time TR equal to 1 by B, and logarithmic decrement lambda equal to BT. Okay. Then lambda equal to capital T by TR. Okay. Thus the logarithmic decrement, logarithmic decrement may also be defined as the ratio of the time period of vibration, time period of vibration, capital T, to the modulus of decay, or relaxation time. Thus the logarithmic decrement may also be defined as the ratio of the time period of vibration T to the modulus of decay or relaxation time. Okay, relaxation time. Our knowledge of relaxation time and the time period therefore helps in the determination of logarithmic or decrement according to the relaxation lambda equal to capital T by TR. Okay, that is relation between logarithmic decrement. Lambda is the logarithmic decrement and the relaxation time TR. Okay, and capital T is the time period. Okay, next is in quality factor are Q values. Quality factor are Q values. Okay, quality factor are Q values. Okay, the quality factor measures the rate of decay of energy of the damped harmonic oscillator. For an undamped simple harmonic oscillator, the total energy, kinetic energy plus potential energy at any time is given E equal to 1 by 2 m omega naught square a square. Okay, the quality factor measures the rate of decay. The quality factor, the quality factor measures, the quality factor measures the rate, of decay, rate of decay of energy, energy of the damped harmonic oscillator, of the damped harmonic oscillator, damped harmonic oscillator. Okay, okay. For an undamped simple harmonic motion, for undamped simple harmonic oscillator, the total energy, kinetic energy plus potential energy, at any time t, at any time t is given by E equal to 1 by 2 m omega naught square a square. Okay, the quality factor measures the rate of decay of energy of the damped harmonic oscillator. For an undamped simple harmonic oscillator, the total energy, kinetic energy plus potential energy at any time t, is given by E equal to 1 upon 2 m omega naught square a square. In the case of damped oscillator, the work done against the retarding or resistive force is not stored as potential energy. As a result, as the particle oscillates, the total energy goes on decrement. The amplitude of the damped oscillation is okay. In the case of damped oscillations, in the case of damped oscillations, the work done against the retarding oscillations. In the case of damped oscillation, the work done against the retarding or resistive force is not stored as potential energy, okay, potential energy. As a result, as the particle oscillates, as a result, as the particle oscillates, the total energy goes on. The total energy goes on decreasing. The amplitude of the damped oscillation, the amplitude of the damped oscillations oscillations is given by a equal to a naught e to the power minus bt. Okay. In the case of damped oscillation, the work done against the retarding or resistive force is not stored as potential energy. As a result, as the particle oscillates, the total energy goes on decreasing. The amplitude of the damped oscillations is given by a equal to a naught e to the power minus bt. Okay, and omega is replaced by by under root omega naught square minus b square equal to omega dash. Energy of the damped oscillator is given by the damped oscillator is given by 1 upon 2 m omega naught square a naught is omega dash square a naught square e to the power minus 2 bt, that is e naught e to the power minus 2 bt, e to the power minus 2 bt. Okay, that is e naught e to the power minus 2 bt, where e naught equal to 1 by 2 m omega dash square a naught square. Okay, when t equal to 1 by 2v, then energy equal to e naught e to the power minus 2b by 2b, that is e naught e to the power minus 1, that is e naught by e, that is e naught by e in time. Hence, in time t equal to 1 by 2b, that is t equal to 1 by 2, the value of b is 2 m by r equal to m by r. Okay, where r is the damping constant, where r is the damping constant, and m is the mass of the oscillator. M is the mass of the oscillator. M is the mass of the oscillator, and the energy of the oscillator decay to 1 by e. The energy of the oscillator decays to 1 by e naught from e naught. Okay, 1 by e naught from e naught. Okay, and during this time the oscillator would have vibrated. The oscillator would have vibrated through an angle theta. Okay, oscillator would have vibrated through an angle theta. Is given by theta equal to omega dash t, that is omega dash multiply m by r that is omega dash m by r radians. R radians. Okay. The quantity the quantity the quantity omega dash m by r equal to q gives the quality factor equal to q gives the quality factor gives the quality factor gives the quality factor r q value. Okay. Definition. Quality factor definition. Okay. The definition of quality factor. Okay. What is definition? Then thus quality factor is defined as the angle through which the damped oscillator oscillates as its energy decay to E naught by E from E naught. Okay. Q factor. Quality factor. Thus quality factor is defined as the angle in radius. The angle in radians. The angle in radians through which the damped oscillator oscillates as oscillator oscillates as its energy decays to E naught by small e from E naught. Okay, from E naught. Then quality factor defined as, thus the quality factor is defined as the angle in radians through which the damped oscillator oscillates as its energy decays to E naught by E from E naught. Okay, quality factor for mechanical oscillator. And the quality factor for mechanical oscillator. Quality factor for mechanical oscillator. Q equal to omega dash m by r, that is omega dash by 2b. Equation number second. Okay. For an electrical oscillator. For an electrical oscillator. For an electrical oscillator, 2b equal to r by l, where L is the inductance and R is the resistance of the electrical circuit. Then quality factor for an electrical oscillator is omega dash by 2b equal to omega dash L by R. Quality factor in term of energy. Quality factor in term of energy. The energy of the damped oscillator according to equation number first is given by E equal to E naught e to the power minus 2 Vt. Okay. Power dissipation. Okay. Power dissipation. P. Rate of loss of total energy with time. Rate of loss of total energy with time equal to minus dE by dt is given by P equal to minus dE by dt, p equal to minus d by dt, that is 2b e naught e to the power minus 2bt, that is 2be. Okay, minus de equal to 2be into dt, that is 2, the value of b is r by 2m e into dt, that is r by m e dt. If dt equal to capital T, the time period of the oscillator, then dt equal to capital T equal to 2 pi by omega dash, 2 pi by omega dash, hence omega dash, hence loss of energy during the time of one time period, or loss of energy per cycle, loss of energy, loss of energy per cycle minus det equal to r by m e capital T, that is r by m capital E 2 pi by omega dash. Okay, then omega dash m by r equal to minus 2 pi e by det. Okay, but det, okay, but omega dash m by r is the quality factor as proved in previous. Okay, is the quality factor, okay, quality factor. Okay, then QF quality factor equal to 2 pi multiply energy of the oscillator, energy of the oscillator whole upon energy last per cycle, energy last per cycle, energy last per cycle. Okay, energy last per cycle. Okay, where energy last per cycle, where the quality factor Q equal to omega dash by 2b, where 2b equal to r by m for mechanical oscillator, and 2b equal to r by l for electrical oscillator, that is mechanical oscillator, that is electrical oscillator. Okay, the quality factor Q is large if damping coefficient B is small. Okay, the quality factor Q is large if damping coefficient is small. Okay, quality factor large, then damping coefficient is small. Okay, small, and Q is small, the damping coefficient be large. The quality factor there represent the efficiency of the oscillator. Hence, lower the damping, higher is the quality factor. Hence, lower the damping, higher is the quality factor. Okay, next heading, effect of quality factor on frequency of oscillators. Okay, effect of quality factor on frequency of oscillator. Effect of frequency of oscillator. Effect of quality factor on frequency of oscillator. Okay, effect of quality factor on frequency of oscillator. Okay, the value of omega dash is given by under root of omega naught square minus b square. When the damping is small are the other word. The quality factor is large, B square is negligible as compared to omega naught square. When 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 the quality factor when the quality factor Q is large. When the quality factor Q is large, then B square is negligible. Negligible as compared as compared to omega naught square, and hence omega dash equal to omega naught. Then QF quality factor equal to m omega dash upon r, that is m omega naught by r, that is m by r s by m whole to the power 1 by 2. Okay, m omega dash by r, m omega naught by r, that is m by r s by m whole to the power 1 by 2, where under root of s by m equal to omega naught, s being the spring constant and m be the mass of SHM oscillator, as m by r s by m whole to the power 1 by 2 equal to alpha constant. Okay, a constant. Okay, and the quality factor is constant, and the quality factor is constant, then omega dash equal to omega not equal to a. Okay, constant. Okay, constant. Then a large quality factor has little. Quality factor has little. Quality factor has a little or no effect on the frequency. No effect on the frequency. Okay. No effect on the frequency. That means the value of omega dash is given by omega dash equal to omega naught under root omega naught square minus b square when the damping is small, or in the other word, the quality factor is large. B square is negligible. As compared to omega naught square, and hence omega dash equal to omega naught. The quality factor Q equal to m omega dash by r, m omega naught by r, because the omega dash equal to omega naught, then m omega naught upon r, that is m by r, the value of omega naught equal to s by r whole to the power 1 by 2, s by m whole to the power 1 by 2, where under root s by m equal to omega naught, and s being the spring constant, m the mass of the simple harmonic motion. Okay, that is m by r s by m whole to the power 1 by 2 equal to a constant. The quality factor is constant as omega dash equal to omega naught, or a constant. Then a large quality factor has little or no effect on the frequency. Okay, that means the value of large quality factor has little or no effect on the frequency. That means if the quality factor is very high, then frequency is 0. If the quality factor is very high, then frequency is 0. Frequency approximately 0. Okay, that means no effect of the frequency. Next is your amplitude, energy, logarithmic decrement, and relaxation time in terms of quality factors. Okay. amplitude, energy, logarithmic decrement, and relaxation. Okay. Amplitude, energy, logarithmic decrement, and relaxation. Okay. Amplitude first. Amplitude. Amplitude. Okay. The amplitude A at any instant time is given by A equal to A naught e to the power minus bt. A equal to A naught e to the power minus bt. Okay. And quality factor Q equal to omega dash upon 2b. Okay. Where V equal to omega dash upon 2q. Okay. Substituting we have A equal to A naught e to the power omega dash t whole upon 2q. Okay. And second point, energy. Okay. Second point, energy. The energy of the oscillation E equal to 1 by 2 m omega dash square A naught square e to the power minus 2 bt. Okay. Equal to 1 upon 2 m omega dash square A naught square e to the power minus 2 omega dash upon 2 q. Okay. Equal to E naught e to the power minus omega dash t upon q. Okay. E naught equal to 1 upon 2 m omega dash square A naught square. Okay. So E equal to E naught to e to the power minus omega dash t upon q. Okay. Next point, third point. Logarithmic decrement. Logarithmic decrement. Okay. Lambda equal to bt. That is b2 pi upon omega dash. That is pi upon q. Okay. But q equal to omega dash upon 2b. Q equal to omega dash upon 2b. Okay. That is t equal to 2 pi by omega dash equal to pi by q because q equal to omega dash upon 2b, then omega dash upon 2b. Okay. Then 2b equal to omega dash by q. 2b equal to omega dash by q. It is cancelled out and pi by q is left. Okay. And fourth point, relaxation time. Okay. Then tr equal to 1 by b, that is 2q by omega dash. Okay. Where q equal to omega dash upon 2b. Okay. Okay. Thank you. Quantitative measurement of damping effect. Okay. Quantitative measurement of damping effect. Okay. The equation of motion of damped simple harmonic oscillator is given by the equation of motion, of a damped simple harmonic oscillator is given by m md square y upon dt square plus r dy by dt plus sy equal to 0, or d square y upon dt square plus r by m dy by dt plus s by m into y equal to 0. Okay? md square y upon dt square plus r dy by dt plus sy equal to 0. md square y upon dt square plus r by m dy by dt plus s by m y equal to 0. Okay? That is d square y upon dt square plus 2b dy upon dt plus omega naught square y equal to 0. Omega naught square y equal to 0. Okay? D square y upon dt square plus 2b dy by dt plus omega naught square y equal to 0. Okay? That is where 2b equal to r by m and omega naught square equal to s by m. Omega naught square equal to s by m. Okay? The factor 2b is defined as the damping force per unit mass per unit velocity and is called the damping coefficient. Okay? Factor 2b is defined as the damping force per unit mass per unit velocity. Defined as damping force per unit mass per unit velocity and is called damping coefficient or damping factor. Damping coefficient and or a damping factor okay, and is quantitative measure of damping. The value of V can be determined experimentally by the following method. Okay, first is by logarithmic decreement. Okay, logarithmic decreement. Okay, logarithmic decrement. By logarithmic decrement. For a damped oscillator, the amplitude decay exponentially with time in according to the relation for a damped oscillation. The amplitude decay exponentially with time in accordance with the relation with the relation a equal to a naught e to the power minus bt. Okay, if a1, a2, an minus 1, an are the successive amplitude if a1, a2 dot an minus 1, an are the successive amplitude, then are the successive successive amplitude, then a1 upon a2 equal to a2 upon a3 equal to an minus 1 upon an equal to e to the power bt, okay, e to the power bt, then log an minus 1 upon an equal to bt, that is lambda. Okay, lambda is a constant known as logarithmic decrement. Okay, where lambda equal to logarithmic decrement, okay, the value of lambda is determined by comparing two amplitudes which are n periods apart, so that a naught upon an equal to e to the power n lambda. Okay, a naught upon n equal to the a to the power n lambda, or n lambda equal to log a naught upon an. The value of b is calculated from the value of lambda and t, which can be determined experimentally. Okay, the value of b is calculated from the value of lambda, and t, okay, which can be determined experimentally, determined experimentally, okay, okay. Next, by relaxation time, okay, by relaxation time, okay, by relaxation time, okay. The value of damping coefficient b can be determined by finding the relaxation time t, the time in which the amplitude of a damped oscillation falls to 1 by e of its original value, by using the relation b equal to 1 by tr. Okay, the value of damping coefficient, the value of damping coefficient, b can be determined by finding the relaxation time, the relaxation time. Finding the relaxation time. Finding the relaxation time TR is that the time in which the amplitude the time in which the amplitude of the damped oscillation in which the amplitude of the damped oscillation the amplitude of the damped oscillator the amplitude of the damped oscillator falls to 1 by E of its original value of its original value by using the relation by using the relation B equal to 1 by TR okay. The value of TR is experimentally determined by plotting a graph between amplitude and time, finding from the graph the value of time T equal to TR, okay. The value of TR is experimentally determined by plotting a graph between amplitude and time and finding from the graph the value of time T equal to TR in which the amplitude falls to 1 by E equal to 0.368 of its original value okay. Third point, by quality factor Q, okay, by quality factor Q equal to omega dash M by R equal to omega dash by 2B, okay, but omega dash equal to 2 pi by capital T, where capital T is time period, okay. Then Q equal to 2 pi by T into 1 by 2B, that is pi by BT, okay, from which we have damping coefficient from which we have damping coefficient B equal to pi by QT, okay, B equal to pi by QT, and the quality factor Q and time period T can be determined experimentally, and and quality factor Q and time period T can be determined can be determined experimentally. Okay. Thank you. Effect of damping on natural frequency. Okay. Effect of damping on natural frequency. The decay of amplitude of a damped harmonic oscillator with time is called damping. Okay. The decay of amplitude. The decay of amplitude. The decay of amplitude of a damped harmonic of a damped harmonic oscillator with time is called damping. Okay. In the case of real vibratory system, damping depends upon resistive or viscous force. Example, resistance of air. Okay. In the case of real vibratory systems depends okay. In case of real vibratory systems, damping depends upon first resistive or viscous force. Resistive or viscous force. Is that resistance of air. Okay. Second point, structural condition. Okay. Exact friction at the support of a vibratory system like a simple pendulum. Third point, velocity. Okay. Velocity. The damping force is independent of displacement or acceleration but proportional to velocity. Independent of displacement and acceleration dependent upon displacement or acceleration but proportional to velocity. Okay. Okay. The effect of damping on natural frequency is discussed below. The frequency of natural undamped oscillation of mechanical oscillator is given by the frequency of natural undamped oscillations oscillations of a mechanical oscillator is given by f naught equal to 1 by 2 pi under root of s by m. Okay, where s is the coefficient, where s is the stiffness constant, stiffness constant. S is the stiffness constant, and m with the mass of vibrating particle, and m with the mass of vibrating particle, mass of vibrating particle. Okay, the frequency of damped oscillation is given by f dash, the frequency of damped oscillations is given by f dash equal to 1 upon 2 pi under root of s by m minus r square by 4m square, where r is the constant known as damping constant. R equal to damping constant, r equal to damping constant, and f dash is the less than, thus f dash is less than f naught. The presence of damping reduces the natural frequency of the oscillation. The presence of damping reduces the natural frequency okay, of the oscillator, okay. The difference depends upon the damping factor. The difference depend upon the damping factor. Okay, damping factor. The difference depends upon the damping factor. Larger is the value of R, higher is the difference between. If R is higher, if R is higher, then difference between f dash and f naught and smaller is the frequency of the damped oscillator. Okay, and smaller is the frequency, smaller is the frequency of the damped oscillator as compared to the natural frequency, of the oscillator, okay. Thanks. Driven or forced harmonic oscillator, okay. When the harmonic oscillator oscillates with its natural frequency in a medium like air, its oscillations get damped. The amplitude decreases exponentially with time to zero. The order damping force experienced may be friction, viscosity, etc. If the amplitude of the oscillations are to be maintained indefinitely, energy must be supplied externally. Such the oscillation of the body under the action of external periodic force are known as force oscillation, and the oscillation is called as the force harmonic oscillation or driven harmonic oscillator. Okay, the frequency of external periodic force amplitude is not necessarily the same that its nature frequency. Initially, the body tries to have oscillations equal to its natural frequency, but after some time, initial and erratic movement, it ultimately settles down to oscillations with the driving frequency, the frequency of the driving force. Okay? When the harmonic oscillator oscillates, when the harmonic oscillator and the harmonic oscillator oscillates when the harmonic oscillator oscillates with its natural frequency with its natural frequency natural frequency natural frequency with its natural frequency in a medium like air in a medium like air, its oscillations get damped. Its oscillations get damped. Okay? Get damped. Get damped is that the amplitude decreases. The amplitude decreases exponentially decreases exponentially with time to zero. Okay? The other damping forces experienced may be friction. Experienced may be friction. Experienced may be friction. Viscosity, etc. Okay? If the amplitudes of oscillations, if the amplitudes of the oscillations, if the amplitude of the oscillations are to be maintained indefinitely, energy must be supplied. Energy must be supplied externally. Such oscillations and the oscillator is called as forced harmonic oscillator. Okay? Harmonic oscillator or driven harmonic harmonic oscillator. Okay, driving harmonic oscillator. Okay, when the harmonic oscillator oscillates with its natural frequency in a medium like air, its oscillations get damped. The amplitude decreases exponentially with time to zero. The other damping forces experienced may be friction, viscosity, etc. If the amplitude of the oscillations are to be maintained indefinitely, energy must be supplied externally. Such oscillations of the body under the action of external periodic force are known as force oscillations, and the oscillator is called as forced harmonic oscillator or driving harmonic oscillator. Okay, the frequency of external periodic force applied is not necessarily the same that if of its nature frequency. Initially the body tries to have oscillations equal to its natural frequency, but after some initial erratic movement, it ultimately settles down. No oscillation settles down to oscillations with the driving frequency, the frequency of the driving force. Okay. Next, differential equation for forced harmonic oscillator. Okay.